We're going to talk about average bond enthalpies. Okay. Hopefully at the end of this screencast you'll be able to define the term average bond enthalpy and explain in terms of average bond enthalpy why some reactions are exothermic and others are endothermic. We've been talking a lot about the enthalpy of a reaction, delta H, Rxn. And how can we determine that? We've seen several ways so far. Experimentally, meaning doing a calorimetry experiment, measuring the temperature difference, the mass of the solution or the system, and applying the Q is equal to mc delta T. Okay, this is Q equals to mc delta T, and then Q of the kind of system is equal to negative Q of the reaction, and then delta H of the reaction equal to Q of the reaction over the number of moles. Sorry, I wrote on an angle. All right, and then we looked at Hess's law, and that's where we had a series of reactions and treated them as a series of equations and either reversed them, multiplied them, did the same thing to the delta H for the reactions given, and then added them together to get an overall delta H. Now we're going to look at specific bonds, those that are being broken and those that are being formed. And we're going to use something called average bond enthalpies to determine the enthalpy of the reaction. Okay, these average bond enthalpies are experimentally determined. Okay, now when you think about a covalent bond, you really should think about it being an electrostatic attractive force between the atoms, that the electrons of one atom are attracted to the nucleus of the other atom and vice versa. And it's that electrostatic attractive force that holds those atoms together. All bonds that are broken, it requires energy to break that bond. You need to add energy because you're overcoming that attractive force. It is always an endothermic process to break a bond. Always. All right, if we look at a quick example down here, I have hydrogen gas, breaking it up into its two hydrogen atoms in the gas phase. The H change in delta H for this reaction is a positive endothermic 436 kilojoules per mole. I have to add energy to pull those atoms apart and make them single atoms. Okay, this can get more complicated with molecules containing multiple bonds. Where do these average bond enthalpies come from? Well, the enthalpy required to break a bond is obtained by averaging the enthalpy values for the same bond in many structures. So experimentally, they determine how much energy it takes to break these molecules into the gaseous atoms. And then they average them. Okay, because depending on the compound, you're going to have different attractive forces. So these are average values determined experimentally. A very important thing to note, all of these bond enthalpies are determined in the gaseous state. So any IMFs, intermolecular forces, aren't present. We can ignore them. They're going to be so small because these compounds are in the gaseous state. So these calculations only apply for things in the gaseous state. Important. This is what a table looks like for average bond enthalpies. It tells us here that the bond H to H, a single bond, it's going to take 436 kilojoules per mole to pull that apart or to break it. For a carbon-to-carbon single bond, it's 347 kilojoules per mole. For a carbon double bond, it takes 612 kilojoules. So a couple things you should note here. One, the more energy it takes to break a bond, the stronger the bond was. The more energy to break it, the stronger the bond was. Double bonds tend to be stronger than single bonds. Triple bonds stronger than double bonds. Take a look at the average bond length too. If we look at the carbon single bond compared to the carbon double bond, carbon single bond is longer than the double bond, and that's also a trend. The stronger the bond, the shorter the bond. Multiple bonds are stronger than single bonds, okay, all else being equal. Okay, so bond making. If bond breaking is an endothermic process, bond making is an exothermic process. And what we've seen before, this is the same equation we just looked at, it's just reversed. What do we do to the delta H for that type? We change the sign. So it makes sense, hopefully, that bond making is an exothermic process. The other thing to keep in mind is atoms tend to bond to become more stable. More stable things are lower in energy. Okay. Okay, using those bond enthalpies in table 10 from the data booklet, determine the enthalpy for the following reaction. We're looking at methane, CH4, and 2O2 going to CO2 and 2H2O. And what we want to use is, I'll find it. Here's the data book. You'll get sections of this. Might also make you a whole copy of the whole data book, hand it out. But here's the bond enthalpies and average bond enthalpies at 298.25 degrees Celsius standard for different bonds. Okay, and these are where I'm going to get my values from. So we'll move this out of the, almost out of the screen. Whoa. And go back to our problem. First thing we have to do is look at what bonds are actually in these compounds. So, and that requires drawing Lewis structures. Hopefully you remember Lewis structures. Okay, CH4 would look like this. I would add it to 2 oxygen atoms, double bonded O. This goes to make CO2, CO and O. Don't ask me why I drew it like that, I ran out of room. And then 2 water molecules. All right, so delta H of a reaction using bond enthalpies is going to be equal to the sum of the delta H of the bonds broken minus the sum of the delta H of the bonds formed. Take a look at this table again. You notice hopefully that all of these are positive because these are all bond enthalpies to break the bond. All right? So if we look, my CH is 413. That's this bond. My double bond O is here, 498 kilojoules per mole. C double bond O is right here, 746. And then the OH is right here, 464. Okay, those are where I'm getting my numbers from in these calculations. So that delta H is going to be equal to, here are my bonds broken. I have 4 CH bonds being broken, plus 2 double bonded O's being broken, minus 2 COO's being broken, and here's 2 OH's in OH bonds in each molecule. I have 2 molecules, so that's 4 total O minus H or OH bonds being broken. So this is going to be 4 times the CH which is 413 kilojoules per mole. plus 2 times the double bond oxygen, that's 498 kilojoules per mole. That's an 8. Minus 2 times the C double bond O, which is 746 kilojoules per mole, plus 4 times the OH bond, and the OH bond is 464 kilojoules per mole. Put that in the calculator, and I get the delta H of the reaction as negative 700 kilojoules per mole. And that is how we would use bond enthalpies to calculate the average delta H, or change in enthalpy, for the reaction.